I just said, I don't have any ambition to get to the end of this talk. If I get to slide number 20, that's okay. 15, no problem. As long as you kind of enjoy it, learn something from it. So stop me anytime. Please let me know if it is too boring, too fast, unclear. Let's just keep it interactive. Okay, well, I'm going to talk about Russell structure, and I'm going to give kind of a theory perspective on the problem and what I think the best solution is. This is a nice computer simulation of how Russell structures look like. So let me give just an outline of the talk. I'll start with a summary, just so that you know where I'm going with the rest of the talk. And pretty much if you understand this is everything you need to remember from this talk. All the punchline will be given there. I'll start some motivation. I think this is the most important part. If you don't believe this is worth doing it, then there is no point in going on. So I'll try to analyze it critically. And then I'll show you more or less what are the thoughts of people. How do people try to describe this going beyond linear evolution, and why I think that all the concepts of effective field theory are really bestly adopted to address this problem. And I'll show you how kind of the old ways of doing things doesn't really give you as precise results as you would like, but if you do that from an effective field theory point of view, you actually get much better prediction for what the spectrum and bispectrum and any other observable that you're interested in should do, and these are the things that you measure. So if you can predict them well, it means that once you measure them, you can extract more information from them. And then I will conclude. So as I said before, I'm just going to give you the whole summary now, and this is kind of the main point of the talk. There is a whole program. I mean, I guess that this is probably an audience that is quite familiar with effective field theory methods in quantum field theory. They have been extremely successful. They have pretty much dominated the field of particle physics and condensed matter, if you want, for many years. They haven't been, effective field theory approach hasn't been used so widely in cosmology, for various, maybe more sociological reasons, but there is a large potential of using these ideas to address some of the outstanding open problems, and this is kind of a whole program. Today I will start with that part of the program in which I'm using this property to study the distribution of matter in the universe. But of course, we need to get that program going until we will relate something that happened in the primordial universe during inflation to something that we observe in our telescopes nowadays. So the idea is to go all the way from the very beginning to the very end. So there are various steps that one needs to do, and I will mention some of these things and why they're interesting. But you can, once you have the right perspective on the problems, everything kind of falls in place naturally. I will argue why you should bother thinking about these things from a theoretical point of view rather than just throwing everything inside a computer. And I'll try to convince you that there is some fun field theory. If you come more from the point of view that you're interested in the tools being used here rather than the observable and the science, I think you can rethink all of your quantum field theory ideas in a different context, which is not quantum mechanical, but is more closer to statistical physics, but is nevertheless very interesting. Okay, so this is kind of the same plot that I had there on the board, maybe with more cartoonish. So we have some idea that there was some primordial phase very early in the universe that underwent an accelerated expansion. We need accelerated expansion because we want perturbations to be coherent outside of the horizon, so a phase of inflation. And as far as we know, the only thing that this did was setting up some values for a scalar field. I'm going to call it zeta. It's important to use the right scalar field so you're sure these things are not going to evolve when you look to the other side. So this is the right variable to use. So all these perturbations were around in the later part of the universe. The universe started going a decelerated phase of expansion when it was mostly dominated by things like matter or radiation. This perturbation started determining how matter was distributed across the universe. So this zeta eventually stores the distribution of matter and also the distribution of photons. So if you want, the patterns in the CMB is just related to this, and the same for the pattern as a function of matter. This is iterative. This is pretty much what we want to be able to describe, and we want to be able to describe the evolution of this matter. Of course, eventually this is dark matter. Most of the matter in the universe is indeed dark. So probably we want to do another step and say how things that shine, like galaxies or stars, how are they distributed on this method? So we have to go one step forward and say, okay, well, there are some baryons, and these baryons collapse and form galaxies. Those galaxies send us nice signals, so we want to relate matter to this distribution of galaxies. Maybe I should have written here a G rather than an N. And eventually we're really observing this in three-dimensional space. In 2 dimensions is obvious because that depends on which direction you're pointing your telescope to. But you can also see the redshift from a certain galaxy, and from that you can try to deduce what the distance from you is, and therefore you get a 3-dimensional picture of the universe. Relating redshift to distance is a little bit trickier. That's why this requires some additional work to be done. But this is pretty much the upshot. You're relating your ideas of inflation to what you actually see in a telescope, and like that you hope that you will be able to describe what inflationary mechanism took place, what are the properties that I need to have. Once you've done this one for your standard lambda CDM with maybe a cosmological constant and maybe just cold dark matter, you want to do it all over again, considering deviations from that vanilla scenario, which is the favored by the data. So maybe you want to say, well, maybe inflation had some interesting interactions, and therefore the initial perturbations were not really Gaussian. Maybe dark energy is not just a constant. Maybe it depends on time, or maybe it's gravity that is being modified. Or maybe cold dark matter is not really cold. So there is a very long list of possibilities, and as long as you fix one of these, you can again do this exercise in which you evolve what you get at the beginning with what you observe at the end, and you can use that prediction to constrain all of these properties of our cosmological model. So this is pretty much cosmology in one slide. People are doing. Okay, so what's the idea underlying effective field theory? There are various ways of saying it. Maybe a pictorial way of thinking about it is which applies to this case, is that we want to describe the distribution of matter in the universe as a generalized fluid, and I will argue why this is a reasonable attempt. Pretty much the idea is the same that you get on standard fluid. It's just there are a few different technical assumptions that go into it. This is the distribution of matter in the universe. As long as you look from far enough, maybe from the last row, you cannot really see the difference between black and purple here. So it looks like a little bit of a homogeneous amount of color. And so that means that you can disregard the very microscopic properties of whatever makes up this fluid and describe it on large scales as a generalized fluid, so generalized hydrodynamics. This allows you to consistently account for all non-linearities that happens on very short scales, and it's pretty much what we do every time we do physics. There are various scales involved in the problem, things that are much smaller than the scales we're measuring, we just don't know what they are, and so we integrated them out consistently. And so the same way that you describe any fluid, you should be able to describe large-scale structure as well, as long as you're sure that you understand the regime of validity of your description. What I think this is fun is that there is a lot in cosmology in which you study modification of the standard model, and you try to see if you see any hint of them in data. This is a slightly different approach. This is actually our standard model. This is lambda CDM. This is the most common, simplest scenario. And what I'm saying is that there is still something that we don't understand about it. So we should try to spend as much time understanding our main candidate as we spend in proposing alternatives. And this is a little bit the proposal here. As a bonus, you get better theoretical predictions, as I will show. Why bother? I mean, a lot of this, the main issues here is that there is some amount of nonlinear dynamics. There are some scales that are very short, and they are described by the very complicated dynamics that we are not able to treat perturbatively, which is the case pretty much every time effective field theories are useful. So you might just think, well, I just put it on a computer and forget about it. It is true that computer simulations, or in this case, they're mostly n-body simulations, have been very useful to understand the dynamics of the system and to make nice pictures like this one, for example. But there are a couple of ways in which they fall short. One of them is that if you understand how the system evolved, you might become more creative and come up with different ways of extracting information from it. And maybe the only information that you can extract is not just measuring a certain correlation, but maybe you can get you can use velocity or other things to get out the information you're after. And there are explicit cases in which this has been done, for example, for the baryon acoustic oscillations. So if you understand how the system evolved, maybe you find more observables. More observables means more data, and then you will do more progress. You will have more progress. The other thing is that when you do it numerically, it's harder to see explicitly if there is a relation among different parameters, which may be very useful. So this might become explicit. Finally, even computer simulations, despite the fact that computers are very powerful, they cannot solve the actual system. They have to make a large amount of assumptions themselves in order to get to a result in a finite time. And those assumptions are completely orthogonal to the assumptions that you would make from a theoretical point of view. For example, they bundle together 10 to the 8 solar masses and they call it one dark matter particle. Clearly one dark matter particle is lighter than that, but that's what you need to do in order to get the simulation running. So it's hard to understand what effect have these approximations on your final result. So having a different point of view, maybe a different approximation of the same physics is very useful because you can have cross-checks. So simulations are useful, but they're not the absolute truth either. I think it's fun field theory, and maybe I'll try to make some of this point more explicit as I will go on with the presentation, but is really you get pretty much all the features that you get in quantum field theories, and for that matter in statistical field theory. You get the UV divergences, renormalizations, counter terms, various renormalization schemes that might preserve or break some of the symmetries. You get IR divergences and IR safe observables. You get running of coupling constants and RG flow if you want to try to resum it to get more precise things. Renormalization of contact operators, and there is a long list. So it's kind of also a playground for a theorist to rethink these ideas of field theories and how they apply in a different context, which is not special relativity, so it's not really quantum field theory. It's h bar is to 0, but there is some statistical distribution in the initial condition. So it's a slightly different point of view on the usual calculation. Okay. Any questions on? It was kind of the bottom line.
Yes, are you going to go through these ideas?
Yes. Yeah, I will show them explicitly as they come. I just wanted to give you the heads up in case you were falling asleep that at some slide, some moment later, they might come up when you least expect it. So you really have to pay attention the whole time. These are some motivations. So this is kind of more coming from the physics side rather than the methodology side. And I said a few words before the talk, but I will repeat it. What is this large-scale structure that I'm talking about? It's just the distribution of matter in the universe. What does it tell us? Pretty much everything you want to know about cosmology is written in there. There are really two big pillars of cosmology, and this is one of the two. If you understand it, you really understand our cosmology and what we will be able to learn in the near and long-term future. Okay, so this is the same plot that I had here. It looks pretty similar. History of the universe, time is on the horizontal axis, size on the vertical axis. This is the size of our observable universe, or if you want, the Hubble radius. Pretty much everything, so we're here 14 billion years after the Big Bang, and pretty much everything that happened after a fraction of a second, we have a good understanding of what went on, definitely qualitatively, but most of the time also quantitatively. And we know that there was a phase in which most of the universe was made of radiation, and then that redshifted away, so most of it was made by dark matter, and that also expanded away, and now most of it is just some weird vacuum energy that we call dark energy. What's interesting about this, and what I'm plotting here in these red lines, is suppose that you have some wave with a certain physical landscape, 10 meters, that landscape just gets stretched by the expansion, so it's going to move like A. But the rate at which it gets stretched is a different rate from the rate with which the observable universe expands. The fact that those two things are different means that there are phases in the history of the universe in which all of these perturbations, these waves with a fixed physical length, they actually come into our observable universe and we can start measuring them in the microwave background or maybe in the distribution of matter in the universe. And there are other phases in which instead the opposite happens. These waves start becoming much bigger than what we can observe and we cannot see them anymore. This is what's happening right now. So now we are losing information as we speak. So we better hurry up with those cosmological observations. Of course, the rate here is not very fast. The fact that this is interesting, it tells you that if you want to understand what the initial condition for the distribution of matter that we observe now is, we start evolving back, at a certain point you're going to hit this yellow line. And there you're going to ask, so what kind of initial condition can I put here? It's really hard, and this is, if you want, the big problem of the standard Big Bang. It's really hard to postulate any initial condition on scales that are much bigger than the horizon, because it means that no causal physics could ever generate them. So anything that happened here is much bigger than what any physical process in which the speed of light is the largest speed that you have can generate. That's why people postulate, and this is just one of the reasons, there is actually another even stronger reason, a phase of inflation in which these scales were actually inside the horizon at a much earlier stage. So the upshot here is that by measuring things very late, you can actually say something about the laws of physics at energy scales that are much larger than a TeV and a time that is very close to the beginning. So for the purpose of this talk, there's a bunch of fun things that you can say about inflation. I'm just going to assume that someone has chosen a model, given you a prediction for inflation, and I'm going to show you how you take that initial conditions and evolve it all the way to here when you measure things. And if you're able to understand that evolution, then everything that you measure here, you will be able to interpret it in terms of some properties of the inflationary physics. And therefore, interactions at very high energies. Some properties of quantum gravity, if you were to see tensor modes, for example. So pretty exciting. So that was the history of the universe, and this is something that I also mentioned before, that you can think of it as not only being a history of expansion, but also being a history of growth of perturbations. You start with everything easy, very linear, kind of the same everywhere, and that's in fact why we invoke inflation. That's exactly the type of physics that we want to describe. And so if you go early enough, or at large enough scales, everything is just described by just linearized equation and waves. And that's the reason why when you look at the CMB power spectrum, you just see acoustic oscillations. So relatively simple physics, just harmonic oscillators in an expanding background. Things get more complicated if you wait long enough or look at smaller scales, and there is a lot of non-linearities going in there. So this is really the hard part of the problem from a theoretical point of view. Interesting observations for pretty much a different reason follow kind of a similar structure. Observation that made very good measurements of the microwave background, and they're still lagging behind as far as large-scale structure are concerned, but this is going to change in the next few years. So we are almost measuring everything that we have to measure here, especially as far as initial conditions are concerned, while here there is still a lot that we can measure and that we haven't accessed yet. And this is going to happen. People are investing billion and billion of euros in trying to do this measurement. So we need to have a theory to interpret that data.
So, going back to what you asked before, so what do we learn by learning more about that? I mean, what are the information? Because I understand why we do CMB, for understanding this large-scale formation, right? So what do we learn?
Well, pretty much you can ask all the same questions. So if you're interested about primordial physics, you can ask questions about how many degrees of freedom were relevant during inflation. Is it just one, as it looks now, or maybe we have evidence for additional degrees of freedom? For example, the 3-point function is a very good way to tell whether there was only one or more degrees of freedom. You can ask what were the interactions. So everything we know about inflation so far is the equivalent for particle physics of a particle moving in a straight line without anything happening. We just know the 2-point function, just free theory, no interactions. What people are after, they want to see some bang, some collision and explosions. So the equivalent of that would be to see deviations from a 2-point function, so from non-Gaussianities, Non-Gaussianity you can measure in this microwave background by looking at 3 points at a time, but you can do exactly the same thing in large-scale structure. Look at 3 galaxies at a time. So those are the primordial questions. The other big question.
And maybe
that
you should also say that you have more leverage, right?
Sorry?
You have more leverage, right?
Yes.
I mean, it's not just measuring the same number to the same precision. You can really measure it much more precise. That's
You have a larger amount of data, and maybe
Yeah,
at some
exactly.
point I'm going to say that. But the fact that the universe has been given only once, it means that you can measure the initial condition only once. And you can think of the initial condition just as being given at any given scale. In principle, so you have a lot of scales. But our universe has a fixed size, and we cannot see anything that is bigger than the universe. So this is pretty much lost as far as we know. And then there are things that are, very small, and they experience so much non-linear physics that we have almost no way to evolve them backward and see where they started from. Any knowledge of initial condition has been lost. So these are very short scales. And actually there are various reasons why this number is approximately here. Let's say 1 more plus. And this is maybe 10 gigahertz. So we are trying to see, to measure these perturbations. The CMB is a two-dimensional, let me get the numbers right. The CMB is a two-dimensional, this is H inverse megaparsec, sorry. We write it in megaparsec because we often work in Fourier space, but if we are working in real space, this is 10 megaparsec. So two-dimensional survey, and I have 3 orders of magnitude, I'm going to measure 10 to the 6 numbers at most. There's no more than that. I have 3 dimensions, so this is the CMB. If I have large-scale structures that are really 3D, then I can measure 10 to the 9. So I get that much better by measuring the volume. This is, very rough estimation.
Are we guaranteed the result as information?
You can ask all the same
It's a
questions.
very simple question. I mean, whether or not I could imagine between CMB and the LSS, there could be some phase transition that if that happens, then I don't really have any information about the past. I mean, we assume that there is smoothness going between the CMB to LSS. I could have imagined where there are phase transitions. Then effectively, from that, the large scale structure to the CMB, there will be no correlation anymore. This happens in any phase transition. It's first order.
Oh.
So I'm just asking whether or not we know that. It's just we hope that's the case.
Well, no, we pretty much know that cannot happen as far as the largest scales involved are. And mostly the reason is that, suppose that some phase transition happens here. And so maybe I see the CMB. Well, I mean, the CMB really comes from matter domination a little bit. That's a beta. The largest scales that I'm observing in the universe were still completely much larger than the horizon at that time. So any local process taking place inside the horizon cannot change them. People state this result as being the conservation of zeta on super horizon scale. So as far as we measure the large scales in the universe, CMB and large scale structure will be exactly correlated. There are only very weird models in which this does not happen. So. You can assume that there are other degrees of freedom around the universe that we have not measured, and they keep evolving, and they could. I mean, this conservation of zeta is true under certain assumptions. That as far as we know, all particles in the standard model, n-dark matter, n-dark energy satisfies. I actually don't know of proposals in which this would be violated at late times. I mean, of course, they will be sensitive to the same thing in different ways, so you can get rid of some degeneracies.
Okay, so you have to make, but you have to make a number of, you have to make some extra assumptions to relate them. I mean, assuming that everything is smooth, there is no things that we don't know, then they're related. But it's not the theorem.
Right, the theorem has assumptions, exactly. Yeah, if you violate those assumptions, then it's not. And the assumptions are more or less.
Curvaton is an example where it changes at late times, right?
Sorry?
Curvaton is an example where it changes at late times.
Changes at late times.
Yeah, depending on when the curvaton decays. It depends on what you mean by late, of course. Yeah.
Yeah, exactly. But
Right.
by late I meant, Z of after
Ah, okay,
0
before
1000.
CMP function.
So
Okay,
that's
that's yeah, sure.
not okay. That's kind of happens.
Okay, sure. Okay, fine.
So that's why I was saying you can mess up with things here because this is the part in which we don't
Sure.
have an exact Lagrangian, but it's much harder to mess up things at scales that are sub EV because we think we understand the laws of physics at those scales. So the CMB is 0.1 electron volt, so it's much harder to mess around with it. Oh, right, I have this. Okay, so that's kind of the hard problem. Structure information. So, the problem is so hard that you just put it on a computer and forget about it. And this is what it looks like. You start with something very homogeneous, with matter being distributed a little bit everywhere, and you start clumping and forming these dense structures. And here I'm evolving it backward, so you get a feeling of what it would mean to look the universe going back in time. And you see that the structure that we see where there is a lot of empty space and a lot of dense points actually is completely compatible with a very homogeneous universe at early times. So the idea is that we would like to gain some analytical understanding of what's going on in the space. So I stress a lot the point of view in which large-scale structure tell us about inflation and the primordial universe. They actually tell us about the other ingredients of our cosmology. They are probably one of the best probes of dark energy. Dark energy, the way in which we see dark energy is just through its gravitational effect, so how much it makes the universe expand, faster or slower. And so one of the best probes that we have of that is some standard ruler that was generated very early, and this is the baryon acoustic oscillation. And this is pretty much the fact that if you have a galaxy here, you're more likely to find another galaxy 150 megaparsec away from it, rather than 105 or 200. And this BAO has although it seems to be large scale, it has a certain width, and that width is associated with nonlinear effect. So if you want to understand this, you need to understand nonlinear effect to some amount. This is what I was stressing before. Large scale structure are really a probe of the initial condition. So far they are compatible as a probe. What we see there is the same that we see in the CMB. There are small initial conditions, inhomogeneities of the order of 1 part in 100,000. And that 1 part in 100,000 is the same at every scale we look at. So we call that scale invariant initial power spectrum. So far we haven't seen anything beside the power spectrum, primordial. But this is 3D information, so there's going to be much more to be learned. And so that's why I really want to understand it, because in principle we can improve by a lot what we know from the CMB, from the microwave background. Okay, large scale structure. This is what I was mentioning before. If you look very close, you see very dense objects, highly nonlinear. It's the same thing that you would see if you look at water very close by, start seeing molecules, and it's really messy. As you zoom out, then you have a large-scale description that is much simpler. Things are both homogeneous, and you have many fewer degrees of freedom to describe this on large scales, because you could describe it as a fluid. So there are two advantages in looking at large scales rather than small scales. One is that you can use some kind of a general effective field theory, so you can integrate out all these complicated things. That's advantage number one. Advantage number two is that even the effective field theories will be a perturbative one, because on large scales, these are things that just re-entered the horizon, so they have not changed since very early on, and so they must also be very, very linear. And so what I mean by very linear, I mean that the contrast, so how much the density is different from point to point, is a number which is much smaller than 1. Okay, so people, of course, have tried to write down theories for this for maybe 40 years, and I'm going to review what the standard approach is and why I think it's falling short in various respects. I think there are at least 3 big problems, probably more, but I'm going to stress those. So this is a review of the standard approach, so we're all on the same page. We write down a Boltzmann equation, or we can call it Vlasov equation in this context. From that we derive fluid equations that are valid before shell crossing, and there will be 3 problems with those equations. One is that it seems more an approximation than an expansion, because we don't understand what the expansion parameter is. Every time you have that, you don't know what your theoretical error is in your prediction. Problem number 2 is actually looks like a pressureless perfect fluid, and we have good physical reason to think that should not be the case. Problem number 3, which depending on where you come from, you could think is the worst or not, is that predictions are cutoff dependent and therefore unphysical, which I would think already kills it, but some people are more reluctant to buy that argument. Vlasov equation, okay, so we have a bunch of, in the universe we really have 6 part in 7 of matter is dark and 1 part in 7 is baryons. As a zeroth order approximation, let's just assume that there is only dark matter. The fact that baryons are baryons and so they're not dark is going to change things on very short scales, where baryons behave differently from dark matter because they start radiating out photons and they can cool. But on large scales, they're all going to behave the same. So as a first order approximation, we're going to assume it's only dark matter all over. I can discuss the expected deviation from this behavior. Okay, so we have a bunch of particles, and we are going to assume that they interact only gravitationally, which is compatible with what we see, so it's really weakly interacting particles. Then from statistical physics, we know that we can describe this by putting a certain density in phase space. We have phase space, x and p, where x is the position and p is the momentum of these particles, and there will be a certain density determining how many particles there are in every little cell of phase space, and that density has to satisfy this equation. This is just the total derivative of f being 0, if you want, version of Liouville theorem. When you write it out, this is what it is. The only input that I have is that the derivative of the momentum is just given by Newton's law, and it's just the gradient of the potential. So this is where I'm telling them that they interact gravitationally. So you can think of these particles at very early times as being, each one occupying a certain position I and having a velocity vi.
Sorry, phi is the gravitational potential.
Yes. Phi is the gravitational potential. And so that is determined eventually using Poisson equation. It will be related to the density.
And pi is just momentum. So you're using basically xp coordinates. So you're using a Newtonian.
Exactly. I'm in phase space, but just for just one more slide, and then I come back to our 3 plus 1 dimensional world. So
that was just the continuity equation.
Because this contains much more, but I'm going to reduce it to the continuity equation right now. This, in principle, is a partial differential equation because there is p and x and t. It's not linear because phi depends on f, and it's an integral partial differential equation, non linear because phi will depend on an integral of f. So it's really hard to solve this. One way that we know that we could find approximate solutions of this as an expansion is by starting to take momenta of this. So we're going to integrate in d3p. We're going to say, well, we're not really observing the velocity of these things. We just see where they are. And we're going to measure things like density or average momentum. So we can take an integral in d3p with various powers of p to capture all the dependence on p. And the first integral of that equation is nothing but the continuity equation. Density at a certain point is going to grow if things fall in, if they flow inside, and it's going to decrease if they flow outside. The second equation that you get is just Euler equation, or if you want, conservation of momentum. It'll just tell you that things are going to accelerate towards the derivative of the potential, pretty much. And this is some Hubble flow, and this is some nonlinear term that you get from that equation. In the standard approach here, you would have some velocity dispersion that relates to higher orders in this expansion, and in principle, this is an infinite expansion that goes to, because it was a partial differential equation, so it should be equivalent to at least infinitely many more ordinary differential equations. The only consistent truncation of this hierarchy is by putting here a 0. If you go to the next order, there is no more consistent truncation. So this is what is usually done. And the standard approach is to say, well, can we try to solve this? So here is where you run into problem number 1, which is what is your perturbation theory? What is your expansion parameter? You would like to say, well, look, it's non-linear. There is delta and v, and here there is v squared. So let's assume that delta and v are somehow small quantities, and we're going to try to do an expansion on that. But that's not really true, strictly speaking. If you were to start with a very homogeneous solution and just let it evolve, you would have particles start falling onto each other, and then they will just pass through each other. And as they pass through each other, this is a phenomenon called shell crossing, they start forming caustics like this. In caustics, the density becomes very large, in fact, formally infinity, and so clearly delta is not small anymore, so it cannot be a good expansion parameter, just delta per se. This is a big problem. It's not just a formality. If you don't know what your expansion parameter is, you don't know the regime of applicability of your theory, and you cannot attach the theoretical error bars to your prediction. So it's really going to make it hard when you compare with experiment to know whether it's your theory failing, is the experiment failing, is evidence of new physics. So you really want to understand those errors. Problem number 2 is that this equation looks like a perfect pressureless fluid. There is no viscosity, no vorticity, not even a speed of sound. That kind of smells wrong. The main reason is the following. So we know that there is gravity, in this system. It's kind of the only thing that there is. We know gravity is non-linear, so it's going to couple the different scales. We understand that on very short scales that undergo this complicated nonlinear evolution and form halos, and then maybe inside halos there are galaxies. We know that those are so highly nonlinear we are not able to describe them perturbatively, so we are definitely missing something. But those things must be coupled to large scales because gravity is nonlinear, so the two things must talk to each other. So you could imagine a process in which a very long wavelength perturbation, which is what they're trying to describe, dumps some energy or momentum into a short scale. So the theory at large scales could never look like a perfect pressureless fluid. It must have some viscosity. It should be able to dissipate some amount of energy. A perfect pressureless fluid is just, it doesn't seem to be the physical right description to have of the system. And in general, you might just be wondering, why don't I have all possible terms compatible with the symmetries of the problem in those equations, as I pretty much always have when I study a physical system. So why are they not there? And maybe problem number 3 is this problem of divergences. So for that, maybe it's slightly more technical, but not too much. So the first thing to appreciate is that when we have loops, that has nothing to do with quantum mechanics. It's just the fact that we are trying to solve a nonlinear equation. So you have a nonlinear equation like box delta equals delta squared, and you invert box, and the inversion of box, you call it g, so just a Green function. So delta is equal to integral of the Green function now when you write delta square, which is an interaction in Fourier space, it's going to look like an integral in K, and this is eventually what we call loop integral. Okay, so this here is non-linear, so I will have all this loop integral, and they will all look like this in perturbation theory. So here, just to show this problem, I'm closing my eyes about problem 1 and 2, and I'm just saying, let's just go ahead and compute, maybe something good comes out. And so you can organize your perturbation theory, starting with just taking first order, and then second order, first order, third order. You always need an even number of them because this is Gaussian fields. So by Wick theorem, if there is not an even number, it's 0. And so you get your would-be perturbative expansion. And you say, well, maybe it works. Actually, you can compute it, and of course, it's formally divergent. If you were to compute as this should be k to 0 and q going to infinity. I'm sorry for the typo. So as you put the momentum inside the integral very large, well, formally, depending on what you put as an initial condition, this could be a formal divergence. Typically, in physically meaningful field theory, you should have a counter term for each one of these divergences, so you would be able to absorb it. No counter term appears in this theory, which is maybe a big problem. What has confused, here you could estimate these divergences by making a simple assumption like that P initial goes like k to the n, if you really want to know when it would be divergent, but it's clear that for a generic initial condition, this would be divergent. What has confused cosmology for many years is the fact that for our particular universe, the matter power spectrum looks like this. So the initial condition that goes inside those integrals looks something like this. So it's pretty much very convergent in the UV and also pretty convergent in the IR. And so people didn't see these UV divergences in their phase. They were doing the integral and getting a finite result. Of course, the fact that the result is finite doesn't mean it's the right result. Everything on this side, which is nonlinear, every time the momentum goes on this side, you're clearly getting the wrong result. So you should have those counter terms to make up for that mistake. And this is the starting point of these ideas of using effective field theory. The short scales that undergo a complicated dynamics, we should integrate them out consistently rather than just throwing them away. And then you will see that each one of the three problems is going to be addressed. In particular, we will have new terms appearing, and those terms will be exactly the counter terms we need, and they will have, you know, a clear physical interpretation.
So, ask an eighth question. On the other hand, we know that we're not putting all the physics are very, very short scales, like a body and system. So why wouldn't be actually physical at all?
Oh, there is going to be a physical cutoff. So there are, yes.
So I understand, I mean, it's nice to have field theories which are well-defined parameters and very short scales, but we know that unless there is a really UV completions, we must deal with a cutoff.
Oh, this theory will have a cutoff. Yeah,
So
absolutely.
you're saying even with a cutoff is a problematic thing. That's
No,
what
maybe, yeah, it's just that there are two things that people could cut out. So usually when you do a renormalization, first you regularize your integral,
Right.
and then you send this one to infinity, and you're still left over with some physical quantity that divides your higher dimension operator, some mass here. Huh? So this is going to be some physical cutoff, and we will have it, and it will be about 0.1 megaparsec, and it exactly comes from this fact that there is some complicated microscopic physics. The way it is done so far is that people were putting this by hand and getting different results depending on what they were introducing here, which is. So exactly, there would be a physical scale, and that scale nowadays is approximately between 1 and 10 megaparsecs.
So sorry, can I ask one more thing?
Yeah.
Maybe I'm actually going ahead. But I mean, if I have an effective field theory with like a perturbation theory, I typically have the theory is not actually strictly speaking renormalized. And the number of capital terms so defined grows with the order of perturbation theory, making the theory less and less predictable. So I mean, would that actually, I mean, maybe it's more precise because clearly it's quite UV corrected, but it becomes also technically unpredictable. You cannot really predict it. Right? In QCD, the effective Lagrange at the end of the day, the coefficients of the effective Lagrange are predicted by QCD, so I can use the lattice to measure the coefficients. In this case, what would I get these numbers from?
Well, I would say it is the same thing that happens in every effective field theory. As long as you are at energy much below the cutoff, for a given precision of your experiment, you just need a finite number of parameters
So
to
you
measure.
have to from experiments.
Exactly. So once you fix them from experiment, you fix two of them. In this case, it will be one of them at Lillingworth, and then you're good. Of course, if you want to push at the cutoff, there is an infinite amount of them, and they just tell you shouldn't use effective field theory when you're at the cutoff. Precisely.
So the question is, you have to, I mean, maybe it's true that you have to hope that there are find an enough small number of counterterms to actually start becoming predictable.
Exactly.
Most often not, that's not the case.
I will show you that this is the case. Actually, with a single number, you can predict one loop power spectrum, and yeah. I mean, I'm going to show you. There is much more data than the number of parameters. Precisely. In principle, we know what the UV theory is, except bariums are complicated, but it's just so complicated we are not able to compute those effective parameters from the UV theory. Okay, so the idea is just a smoothing. It is true that delta is not a good expansion parameter, but if you smooth it on large enough scales, it means that you're kind of averaging out, and we know that things eventually must look perturbative, because on very large scales there are very small differences among different parts of the universe. So if I put some smoothing function, this must be a small quantity, so this is probably the right choice for my expansion parameter. Once you smooth something which is not, when you smooth something linear, you have to smooth, the smoothing of delta is just delta long, just the long wavelength part of delta. But when you do the smoothing of something nonlinear, you get terms where you can pick up some short scale effect that feeds into your large scale. So that's really the hard part. Effective field theory tells you, as long as you have identified the correct degrees of freedom on large scales, everything that comes from the short, you should be able to expand it in the tailored powers of the long modes. And since the long modes are indeed small, that's how we define them, then this is a meaningful Taylor expansion. And here there is a term with delta, and then delta square, and you could have derivatives of delta, so this is an infinite expansion. of course, to any given order in perturbation theory, for any fixed precision, you could stop at some point. Slight difference from what happens in field theory here, you also get a stochastic term, something which maybe I would not mention too much. I will not discuss it too much, just in the interest of time, but if you're curious, you can ask me. Of course, now we will not be able to know what these derivatives are because we don't know what the short modes are, but those are exactly our effective parameters. We can fix them once and forever with measurements, and then the theory becomes predictive. After you do that exercise, well, you can do it two ways. Either you just take the smooth thing and put it on these equations and compute, and you get one result, which is pretty much that. Or you could just say, well, this is an effective field theory. I identify the symmetry of the theory, and I'm going to write down all possible operators compatible with the symmetries. The symmetry are conservation of mass and momentum, homogeneity, isotropy, and generalized Galilean invariance or equivalence principle. And these are all the operators that you can put at leading order in derivative, next order in derivative, higher orders, and so on and so forth. So the two results give you the same, the two approaches give you the same result. This is nice because we see that we have identified the right degree of freedom, delta, which is small, so a right perturbation theory. And now this is not anymore a pressureless perfect fluid. Actually, it has pressures and viscosity, shear viscosity, bulk viscosity, and so on and so forth. So it's exactly as you expected. It's a generalized fluid. All terms allowed by the symmetry appear. And magically, but maybe not so magically, if you're familiar with effective field theory, this is exactly what you need to solve the UV problem. So the problem we had before was that these nonlinear interactions were giving us UV divergences. Now we have new terms. For example, let's concentrate on this speed of sound term. I will not discuss this other just for simplicity. Well, we have this new term that means that I can have a new corrections to my delta. That correction is just integral of the green function, just the inverse of this box. And now I have these two derivatives acting on the and there is a parameter that I'm going to call the speed of sound, just because it has exactly that form. So now I have these new corrections to my prediction for delta, so I can plug it into my prediction for the power spectrum. And therefore, now this is what I had from before, P22 and P13, and as I argued before, those were divergent with some powers, and this was the UV divergent integral. But now I have a new contribution that comes from this new correction. Let us just look at the PCS2 and the P13. You can see that both of them have exactly the same K dependence, plus some quantity that in principle depends on the cutoff. So as you always do in field theory, you introduce a regulator here. The regulator is going to tell you that there is a divergence. You assume that your counter term has a divergent part that cancels the divergences, plus a finite part. The finite part is the one you want to fix. So this is required to make the theory give physical prediction. If you don't have this term, you're really not measuring anything physical. And the same could be made for higher orders counter terms.
Can I just ask a quick question?
Oh, yes.
Actually, on the previous slide, so this bulk viscosity term that you get, yeah, okay, that one. No, even previous. You wrote when you got the.
Yes.
So how do you interpret the bulk viscosity term?
That's a very good question.
Because in principle, this could be dark energy, couldn't it? Or mimicking dark energy.
Yes.
Well, first of all, it's a sum of two terms, so how do you split them in the first place?
Right, yeah, so as long as you work with the, this
One
is,
is front of the time.
exactly, so this is the projection onto the well, yeah, you know what I mean. And so there are these three are non-degenerate at the level of this equation. What happens in cosmology is that, so here you have a vector, so it's three components.
Yeah.
Vectors, it's always convenient in cosmology to decompose them into under spatial rotation, under scalars, transverse vector, and transverse traceless tensors. So the vector will be, V equal D of something plus omega, where this omega has no, it's only a curl. It only has 2 degrees of freedom. In cosmology, this guy, in linear theory, goes like, decays like 1/a. So this is most of the time 0. There is an interesting story here, but the upshot of this, well, let me call this 0. The upshot of this that when you do perturbation theory, you typically assume that V is just, it's a potential, it's a velocity that comes from a potential. If that's the case, here you can take a total derivative without losing any amount of information. You just take the divergence of this, and all of these terms become degenerate with each other. So unless you are able to measure some actual vector mode, bulk viscosity and shear viscosity will be completely degenerate, and you will not be able to tell.
Okay.
This is the most relevant case because we don't measure vector modes in cosmology. If you have more detailed measurements of maybe vorticity in simulations, you can start thinking about how disentangle these parameters, and we can discuss more in detail. There's a whole story about that. But the reason why I didn't point this much out is that actually this one is also degenerate with this at leading order. So at leading order there will be only one parameter out of all of this. This is a specific property of this perturbation theory, is not generic. For a generic fluid, all of them will be relevant.
So is this smoothing a local procedure?
Local on the cutoff scales, yes. So it's, I mean, the smoothing is going to define some scale over which, maybe the best, maybe anyway, I'm going to try to rephrase your question in this way. Eventually here you might ask whether some non-local term should be appearing.
Well, I'm just saying,
Sorry.
if you have a non-local term in the Lagrangian, then you don't know how to discuss normalization. So does this smoothing introduce some non-locality?
Locality, it's a longer story, but the short version of it is that there will be no locality on scales of the order of the actual physical cutoff of the theory. So these higher derivative operators will be suppressed by some scale, which I will argue for our universe now is about 0. I don't know, something like that, H inverse megapascal. So on scales larger than this, there is everything is local. As you get closer and closer to the cutoff, you start seeing some potential for non-locality, but your effective field theory also breaks down. So as long as the effective field theory is valid, the theory is local. And the breaking of locality actually comes at the same time as the breaking of the effective field theory, so you know you have to throw away everything. And this is always the case every time you look at an effective field theory. As you go closer to the cutoff, you will, your perturbation theory breaks down. So locality, unitarity, everything breaks down, but we can just say our effective field theory is wrong there. I mean, it's the same.
In you always have locality.
Sorry?
In current perturbation theory, you have locality.
Yes.
You may not have unitarity, but locality is there.
You have,
Carl Lagrangian is local.
you have one term which is non-local.
Okay, if you have
Depends
a
on
topological.
But you have it. The Zumwitten term which is an infinite term.
But by locality, you mean it's really expressible as a power series of this quantity, of derivative divided by some cutoff. Yeah, that is the case here. Yeah, that is the case here. Yes, yeah. I was just saying that the sum of these infinite terms doesn't converge anymore on those scales and so on. But no, but it looks local. We can discuss exactly how to write it in terms of the right variable to make it explicit. Okay, so kind of coming close to the end of the. Wait, how much do I have? Yeah, 5 minutes. Good. So we can cancel the UV divergences. Of course, I was able to show you the counter terms at the first loop order, but you can see that these things would generalize to any order. As long as you introduce all operators compatible with the symmetries, then you should be able to cancel all divergences. And this is indeed the case. Well, I mean, just to discuss the actual physical consequences of this approach, it is useful to do it in an approximation of our universe in which we forget about the cosmological constant and we say, well, there is only matter. So just all of it is matter. This particular universe called Einstein de Sitter universe is a very good approximation of our universe for a large amount of time. And it has the particular property of having an additional symmetry. The symmetry is called self-similarity, and it relates space and time dependence. if you know a certain solution as a function of space at one moment, you know it at all times, just in an Einstein de Sitter universe. So this is a very useful symmetry to use to study the defective field theory, and you're able to estimate everything on the back of an envelope. When you want to make precise prediction for lambda CDM, of course, we will want to do everything numerically with the cosmological constant. But this is just to get the feeling for what happens. The main upshot is that because of this symmetry, all results, you should be able to write them as ratios of a space-dependent thing, like momentum, with a certain time quantity, such that this ratio is invariant under the symmetry, because the final result must be invariant under such similarity. And this k nonlinear is a specific time-dependent quantity that has been derived exactly to have the right scaling, such that this one does not depend on time. This means that I will be able to write, now I'm going to try to make some prediction from this theory. The prediction we made a statistical prediction, like 2-point correlators, 3-point correlators. And this is the 2-point correlators. And I know at the lowest order should just be the result that I get from linear theory. So if I'm assuming of starting from a power spectrum that goes like k to the n, if I multiply with a k cube, which is the definition of delta, k cube t, it just goes like this. Now, on the second line are all the usual perturbative corrections to this. 3 to the n to the power 2, 3 to the n to the power 3, and so on and so forth. These are the standard perturbative corrections. Now, because I have these counter terms, I will have new possible exponents. One of them is just coming from 2 more derivatives of this. This is the equivalent of the speed of sound or the viscosity. And then there is another one that I'm not going to discuss. So we can see that this is now it's explicitly an expansion in k over k nonlinear. And so as long as we're looking at scales that are much smaller than this nonlinear scale, whose value in our universe today is approximately this, then this is a convergent expansion. You can think of these additional operators or these additional effects in the power spectrum as being a higher dimension, if you want, irrelevant operators. And if you want to be more precise, you can include more of them. Of course, when k is over the k nonlinear, everything goes out of the window. So what we did here, you can think of this as being a plot of the dimensions of various operators as function of the initial power spectrum. In our universe, the relevant power spectrum actually has a slope at the relevant scale, which is approximately minus 1.5. But here we did it for all n using dimensional regularization. So here, the lower you are, the least irrelevant you are. So of course, the first one is this linear perturbation theory. That's the basic one. Then 2 derivatives above that is just the speed of sound, and so on and so forth. And then you get other corrections, like 1 loop, 2 loops, 3 loop, etc. If we fix the value of n for the one that is relevant for a universe, minus 1.5, this tells you what is the order of corrections that you should include for consistency. In particular, if you were to include the 2 loop corrections without including the speed of sound, you wouldn't be converging to the right result because you skipped one order in this expansion. And this is maybe the most explicit way to see that you need these effective corrections in order to get the right result. And we will see this in a plot in a minute. Okay, this is the plot. Power spectrum divided the actual result from a simulation. So let's assume that the result from the simulation is just the reality. So you really want to be as close to 1 as possible. And here we are showing maybe 3% deviation. Actually, this is taken from Carrasco et al. As a function of scale. As you include shorter and shorter scales, eventually you're going to mess up because you're getting closer to your cutoff. You're including too much nonlinear scale. All the dotted lines are the standard perturbation theory. One of them is 3 level, one of them is 1 loop, one of them is 2 loops. I cannot even tell which one because it's not a convergent expansion. You see that even if you go to 2 loops, you're still messing up your prediction very early. When you do this effective field theory and account for all the terms consistently, actually the prediction, well, 1 loop, you're able to predict up to scales that are much larger, maybe a factor of 3 as large, and 2 loops, even larger scales. The presence of these oscillations has to do with bioacoustic oscillations and IR resummation, and it's something I didn't have the time to discuss, but it's less than 2%. So this is indeed a convergent expansion.
Sorry, but you had these counterterms you had to fit.
Yeah, exactly.
So
So
what you fitted it?
they're fit, so the 1 loop is fit using all the data up to here, and then in the 2 loop the same value is used. So there is
the
this
question
in-
one could ask is whether or not you're actually predicting rather than fitting it.
Exactly. So
So it's a different story, because I mean, you will still say that the numerical, we consider numerical calculations to be now the truth. I mean, that in principle contains every effect.
yes.
But in the effective Lagrangian, you will have this ignorance of this counterterms, of the defining part of the counterterms that you have to fit.
Absolutely.
So I would say that the success you're saying is in the fact that the two loops, you can go a little bit further because you're fixing the coefficient basically in one loop left.
Yeah.
Open, and at two loops, no new counterterms emerge.
Exactly.
Because otherwise, it's otherwise the prediction is,
Otherwise, you would have
it's a cheat, right?
more terms. Yes. I mean, of course, there are fitting parameters, but maybe two approaches. One is that we know that there is some part of the physics we are not computing. So if I come with a prescription in which there is just zero fitting parameters, somewhere I'm making an approximation and I'm not exactly telling
I'm
you.
not justifying it.
Yeah,
It's
yeah.
a grand spectrum. I'm just saying that technically speaking, you're paying a toll for the effective theory because introducing counterterms, you have to fit with the experiment. So that's what
Exactly. You lose
so you
predictive
somehow you figured the speed of sound in such a way that the model was giving some decent result,
precisely.
and that using that for potential application to loops. What you have shown, and I believe you said that the loops are not new counterterms, you still have to fit. Because if there were new counterterms still to fit, technically it's still not a prediction.
Mm-hmm. Yes. Yeah, it's a long discussion, the one of the two loop, and there's a lot of topology involved, and we can discuss it offline. The other thing that you can do, instead of going to two loops or to even shorter scale, you can look at higher correlator, like the 3-point function. And that's what we did. There you do have new counterterms, but you also have a much larger amount of data. Maybe I'm going to show you a plot. And you can see that even there is some amount of consistency. Of course, you're paying a price. Nothing comes for free. That's a good point to make. Yeah, this is what happens when you get rid of this oscillation. That's something I haven't discussed, so I'll just keep it. Maybe this is just a different way of doing it. If you can go on with this procedure and compute the higher endpoint correlations, which are relevant for observations. One that maybe I mentioned a few times is that we really want to know if the primordial perturbations are Gaussian or not, so we need to compute a 3-point function. And indeed, for a 3-point function, we have 3 new operators, so 3 new effective parameters that we need to fix. And these are some of the graphs that go into the calculation, just to show you that we did some work. The interesting thing about the 3-point function is that the 3-point function is a function of at least 3 variables. So it's not just one line that you can fit by going a little bit higher or a little bit lower. It has some structure that you cannot change arbitrarily. So if you didn't have the right counterterm and there was a bump somewhere, you just would never be able to fit. And this is some of the structure that you get from the tree level and from perturbation theory. And the one that you get from the counterterms take these shapes. It's something that you can go and plot. And then you can see whether you perform better. So here what I'm showing you is the chi-square divided by the number of degrees of freedom of a certain set of data, including shorter and shorter scales, as compared with a theory. So you want to be as close to 1 as possible. Again, standard perturbation theory becomes is not a good description of the data pretty early. And here you get, depending on various versions, that I'm not going to discuss this detail about this counterterm, but the effective field theory is able to predict up to scales that are at least twice as short as the one in which the standard perturbation theory fails, and you can just reformulate that in terms of a p-value. P-value just tells you what is the probability that the data is a random realization of a theory. And for standard perturbation theory, that probability is 0 pretty early, while for the effective field theory, the probability is of order 1, 50% or something, up to scales that are much shorter. This means that if you're doing experiment and you use this approach, now you can use the data all the way to here rather than stopping here. A very naive way of saying that you gain a factor of 2, and therefore there is maybe a factor of 8 more numbers because it's a 3-dimensional one that you can gain. It's actually a little bit less than that because there's some non-Gaussian errors, but more or less, you do gain a lot by going to shorter and shorter scales. So you're really extracting more information. Okay, let me conclude. There are some features of standard perturbation theory that are unsatisfactory. There is no clear expansion parameter. It looks like a perfect pressureless fluid, and there is no reason for that. And there are explicit UV divergences that make the prediction unphysical. So the effective field theory approach just addresses this by doing what you would do all the time in field theory, just put the right counter terms that are required by the simulation. There are a couple of advantages. One is that you get, so that's a big one, you get physically meaningful prediction. Number two is that actually those predictions convert to the right result, rather than being an unconvergent expansion, as in the case of standard perturbation theory. Of course, you have to pay a price that you have fitting parameters. There are some discussions that can be done about the fitting parameters appearing in the bispectrum that I will be happy to discuss with you. And then you can reach much shorter scales, and therefore having not really 8, but maybe 5 or 6 times more modes to measure. So the outlook is that we want to keep extending this theory to including bias and redshift space distortion. And maybe there is some work to be done in understanding the value of this coefficient from some simplifying assumption of the UV theory, the same that you were mentioning could be done for QCD and the chiral Lagrangian. And there are some ideas about this that I'm happy to mention. And of course, we want to introduce non-Gaussianity, modifications of gravity, and so on and so forth. Thank you very much for listening.
So when you say right result, you mean the numerical simulation.
The right result.
When you say right result, you mean the numerical simulation.
Yes. Yeah.
So the question is how reliable or how reasonable are these numerical simulations in the nonlinear regime? Because that is with you are comparing your loop corrections to it.
Yes.
So
Absolutely.
you also have to have some idea about the numerical simulations for the nonlinear scales. So
Yes.
how reasonable are they?
And numerical simulations are really not expanding in perturbation theory. So in principle, there is no obvious obstacle to go into the nonlinear regime. The main approximation that you do in n-body simulations is that you cannot describe too many particles, so you put a lot of them together and just call them one particle. And sometimes a lot means a lot, like 10 to a very large number, like 10 to the 8 solar masses, where already a solar mass would have 10 to the many dark matter particles. That, of course, is not the right thing to do, but as long as you look at large scales where most of what things do is just following the gradient and moving towards maybe and eventually viralizing the system, there is not a very large error. Depending on the number of particles, the resolution of the simulation, there will be a scale beyond which your simulation does not give you the right result. And this is usually estimated just with convergence test. They double the resolution or they double the mass scale, and they see if the result is the same, and then they call it convergent.
No, because you mentioned that you are trying to compare the loop correction result, like within 1% to 2% of a numerical simulation.
Yes.
But if they're like a few percent error within the numerical simulation result themselves, then it's not really a correct comparison to the numerical simulation result.
Absolutely.
So
Yes. The expectation is that via convergence test, the state of the art of numerical simulation should be of the order of 1% or maybe a couple of percent, and hence the error bars in those plots. This is what the numerical simulation community argues, and that's mostly based into us computing somewhat different codes and mostly just doing convergence run. You keep getting the same number as you change the parameter, you think that must be the right number. Of course, there are issues about that, but that's where it comes from. So people claim 1 or 2% error bars for simulations. So that's why it was meaningful, that comparison.
Sorry. So basically, can you be really more competitive than the numerical ones? And there are data coming out from LSS. Will this approach in the end being more competitive than, assume that the people doing supercomputers get a bigger computers, which they also do, right?
Yeah, absolutely.
Standard load and every year so would actually in fact be able to be more competitive or complementary. So what would you say?
Yeah, the practical use, yeah, of course.
It's just a question of cost efficient.
Yeah, yes, exactly. So,
So want to win.
exactly. Beyond the fact that you actually understand what you're simulating rather than having a black box, you might ask, can I actually use this in practice when I analyze data? And for the power spectrum, I think it would be hard. Probably the numerical simulation are still an efficient way of doing it. But there is something that is needed every time you measure things like the power spectrum. You need the variance of the power spectrum, which is the tri-spectrum. And that's very time consuming to extract from simulations because you don't have enough statistics and you have to do it for a lot of configurations. So for things like that, this type of approach might actually give you a much quicker way to estimate it. So that's something we're working on.
So you get around a factor of 2 or something like that. What about these renormalization group approaches and all these other approaches there? How does it compare to that?
Yes, I don't think that there is. It doesn't buy you much. I mean, we estimated and we have a little comment on that. It allows you to resum some infinite series, some very specific infinite series of terms, but they are the same order as some higher derivative terms that you are neglecting in the calculation. So it's not clear it's a fully consistent way of doing it. You might be, just partially resum a certain term. So it doesn't seem to buy you much. This is my understanding.
But what if you, I'm just curious, what if you plot their results in the same way as you plotted the two loop and the effective thing? How would it compare?
I haven't plotted it. I mostly was kind of working from the point of view that unless I think this is the right thing to do, I'm not going to try to compare it with data and convince myself that even if I don't know why it works. So I didn't really compare it because I thought it's not consistent in a perturbative expansion. Maybe there is some kind of word and hand-waving argument that you can attach to it to convince yourself that maybe you're capturing something, but it's a little bit tricky. It has to do with what you think is breaking the effective field theory and whether it is nonlinearities or shell crossing. So it's maybe a little bit of a more complicated issue. My impression is that you don't gain much. Maybe some people tried it explicitly and maybe there is a little bit of an improvement. I actually don't know that. It's a good idea.
No, it's just curious because I think Scocimara and Petroni and other people have been trying these approaches, right?
Well, those approaches are definitely interesting, but one of the major problems there is that they're resumming certain terms, the one that they are able to, certain diagrams, but there are specific symmetry in this system. In particular, one of them is this equivalence principle. So if you only resum a certain set of diagrams, and each one of those comes with another one with exactly the same value and a minus sign because of symmetry, you're clearly not capturing anything true. And I think that there are explicit calculations that show exactly that some of the infinite resummation that they do is exactly cancelled by the infinite amount of terms that they do not resum because of Galilean invariance.
Because I would have, so I don't know about that, but I would have imagined that they would have argued that they are resumming the right things, but you're saying they're not.
They are not because their resummation explicitly violates equivalence principle or generalized Galilean invariance, however you want to call it. I can show you a paper by a postdoc at Princeton in which he actually takes all the diagrams that should be related by Galilean invariance, resums them, and show that you exactly get minus of what they resum. So I find that pretty convincing, besides the argument about the symmetries.
So you're saying they will be in order, their approaches will break down at the same time as the two loop or whatever.
Yes, yes. My understanding of what they are doing is that, if there is some improvement, it's not clear exactly where it comes from. My opinion.
But is that, now you said that dubious, because you're saying if there is some improvement, it's not very clear where it comes from. I understood that you said there is no improvement.
I don't know phenomenologically, I haven't looked at those plots and I haven't seen people comparing them explicitly. And also I don't want to talk for Roman's predictions. At the leading order, a k-square term, everyone gets it. The question is, what do you expect it to be? Can describe them.
If there is no more questions, thanks.